So, good morning students. So, we are discussing the applications of the Gauss law. So, here today let us discuss about the self energy, and we know already about this potential energy. In potential energy generally there may be two terms may be there. When only point charges are there, and previously we discussed about the potential energy of the point charges. When only point charges are there, when they are interacting with each other, then we write like suppose if these 2 point charges are there here separated by a certain distance r, then potential energy of the system is nothing but we write like k q1 q2 by r, right? And so now that energy is nothing but we called potential energy, and in that potential energy only we call that as interaction energy, right? Because when only those two charges are there together, then only that amount of energy will be there. If we are removing one of the charge, then there is no energy for that system. You can't define the energy for that system, right? If this Q2 is taken to that infinite and only Q1 is there, then its energy we can't define for that. And that means if the point charges, isolated point charges are there, you can't define the potential energy. When they are interacting with any other charges, then we can define the potential energy of the system, right? But that is not the case for these charged objects. Like if a sphere, charged sphere if you are taking, or if you are taking a charged spherical shell, if only spherical shell is there, then it possesses energy, even though any other charge is not there in its surroundings. If only charged sphere or charged shell, they are there, isolated charged sphere is there, then isolated charged sphere can possess certain amount of energy. And that energy is nothing but actually we call this self energy. So self energy. So self energy is nothing but we can define it as, if suppose if you are charging a spherical shell for example, so then we are giving certain amount of positive charge to this. So when you are giving certain amount of positive charge here, then suppose during the charging process at any instant already Q is the charge given to this. Now we are adding the charge, we are increasing the charge, we are adding the charge dq here. From by external source we are bringing the dq and we are giving to the charge to this shell here. Now already there exists some positive charge here. Now this incoming charge is also positive. Then there exists some repulsive force between them. And so that repulsive force is nothing but against that repulsive force, now we need to do certain amount of work here. And so that amount of work is nothing but will be stored as energy in that system. So that means we can define it as the amount of work done in charging the object. So whenever you are charging an object, then definitely certain amount of external work done is required. So the amount of work done in charging the object is nothing but that will be stored as energy in that system. So that energy is nothing but we call self energy. So self energy in the sense, even though surrounding no charge is present, that object will possess certain amount of energy there, right? And so now here we can also explain the self energy in another way. So self energy is also one type of interaction energy we can say. Like interaction energy means suppose on this sphere I am taking one element here. Suppose it is some charge dq is there here. Then another element of charge suppose I am taking here. That also let us take identical element so that dq charge will be there. Now there exists some interaction between these two. Interaction in the sense some force will be there. It may be attractive or repulsive, that depends on the nature of charges. So in this example you can say that force will be repulsive force will be there because both are like charges. So that is nothing but whenever either attractive force or repulsive force is acting between the charges, you can call that as interactive force. They are interacting with each other. And so now here these two are interacting with each other. So whenever two charges are interacting with each other, that possesses that amount of energy, right? And so for these two elements also we can define such an amount of energy. And so that every element will interact with every other element in that object. So if you are assuming that spherical shell is made up of large number of elements, so every one element of the spherical shell will interact with the other element of the spherical shell. And so that such a type of self interaction energy. So that means interaction between the elements of the same object. The type of energy you can define it as self energy here. So that write the definition. So that is another way here. It is also a type of such an interaction energy. So write the definition for the self energy. The amount of work done in defining, amount of work done in charging the amount of work done in charging the given object is called, the amount of work done in charging the given object will be stored as energy in that object called self energy. It can also be defined as the interaction energy between different elements of the same object. The interaction energy between different elements of the same object is called self energy. And there I mentioned that self energy is not defined for the point charges. That means we can take it as 0. That means when point charges are there, we can't define self energy. We define for the spherical shell and the like such a charged objects, charged sphere. So self energy is not defined for the point charges, or that means not defined in the sense we can take it smallly as 0. The self energy is 0 for the point charges. Now let us write this expression for self energy of a spherical shell. So now I am taking a spherical shell here, spherical shell of radius r. It is carrying, it is finally charged to the charge q. So now we are assuming the state during the charging process. So that means we are adding some amount of charge step by step to that spherical shell. So that charge on the spherical shell is increasing from 0 to a final value q, right? So during that process, we are taking that q be the charge present on this, small q be the charge present on the spherical shell here. And we are adding a small amount of charge dq to this. So we are adding some charge dq to this spherical shell here. So write that, consider a spherical shell of radius r. Consider a spherical shell of radius r. During the charging of the spherical shell, let q be the charge present on the spherical shell, small q. Q be the charge present on the spherical shell at any instant of time, and dq is the charge added to it, Let capital Q be the final charge on the shell. Let capital Q be the final charge on the shell. So now here these two, this Q already, that means existing charge, and this dq, they are interacting with each other. And so they are interacting with each other means then for the small element of the charge we can write that potential energy there. And so therefore for the small element I can write this potential energy as, or the interaction energy as, like k into q by r into dq. Just we are writing it as vq, where v is a potential on the surface we can write, and in that potential this charge is lying here. So that potential energy. And so now this can be written as, now the total self energy we can write it as, the total self energy is equal to integral of this du we need to write here. Therefore I can write this self energy is equal to integral of k cube by r into dq. And this k cube is that means k by r is a constant, so that I am writing outside. Here q is a variable here, because that q value is varying from 0 to capital Q. So just integrate that. Therefore the self energy of the spherical shell is, will get like k into capital Q square by 2r you will get. So this is the self energy of the spherical shell, or which we can write it as, if we substitute that k value, 8 pi epsilon naught r you will get. So this will be the self energy of the spherical shell here, right? So need to remember these expressions. So self energy of this expression actually be derived in the gravitation also. In the gravitation, just you will get like gm by gm square by 2r you will get in case of gravitation, and that will be negative energy in case of gravitation. So then here you will get a positive energy here. That means even though the charge given to this spherical shell is negative, that self energy will be positive only, because here q square term is there here. So that you will get that self energy as a positive term only. So that will be the self energy of this spherical shell. Got it? Now similarly we need to derive an expression for this self energy of the solid sphere, uniformly charged sphere. So let us see that the derivation. Self energy of the uniformly charged sphere. Uniformly charged solid sphere here. So let us take this as sphere of radius r having some charge q. And so now here for this we consider two elements like this. This is sphere, solid sphere of radius r, and surrounding this we are taking another spherical shell element like this, right? So now here two elements are there. This is solid sphere of radius r, that is one element, and the surrounding this spherical shell, this part. So this part we consider as another element here. So its width is dr, right? So first write that. Consider a spherical solid sphere of radius r. Consider a solid sphere of radius r having charge q distributed uniformly. Having charge q distributed uniformly throughout its volume. Throughout its volume. In that, consider a small element, small solid sphere of radius as one element. Consider a solid sphere of radius r as one element, and the surrounding spherical shell of radius r and width dr as another element. Let q1 and q2 be the charge in those two elements respectively. Let q1 and q2 be the charge in those elements respectively. So we are taking that charges as q1 and q2. So first let us write the expressions for this q1 and q2. So first I am writing this q1 expression. Just we can write it as charge density into volume, because it is uniform charge distribution only. So charge density you can write as q by 4 by 3 pi r cube, volume of that solid sphere. So it is 4 by 3 pi small r cube. So therefore I can write this q1 is equal to q into r cube by capital R cube you can write. This is q1 expression. Next similarly write this q2. Therefore this q2 is nothing but again same volume charge density 4 by 3 pi r cube into this 4 pi r square 4 pi r square into dr, volume of the spherical element. We written in many problems or many cases. So this surface area into width of this element. And so now therefore you can simplify this as 4 pi will be cancelled. So 3q r square into dr by capital R cube. So now that is that case here. Now these two are interacting with each other. Those two elements are interacting with each other. So let us write the potential energy between them. And so now that du I can write as potential energy for these elements we can write as. So then you can observe this total charge q2 which is enclosed in the spherical shell is lying in the potential produced by this one we can consider here. Like that means we are adding such a spherical shells here. What actually we are taking is we are adding such a spherical shells to get this complete sphere. That means initially suppose this part is there. we are adding another element like this, we are adding another element like this, we are adding another element like this. So such a elements we are adding here, spherical shells we are adding here, so that you will get this complete sphere, right? And so that means now this shell is present in the field or potential produced by this already existing solid sphere here, right? And so that potential we can write as Q1 by 4 pi epsilon naught R. This is a potential due to the solid sphere on its surface. In that potential, this Q2 charge is there. So this is Q2. So it is a interaction energy between those two elements there. And so therefore we can write this as the total self energy I can write as integral of this du. And so therefore the self energy is equal to, now we can substitute those Q1 and Q2 values there. And so Q1 is given by this, I am substituting that. Q r cube by r cube, capital R cube, into this is 3q small r square into dr by r cube by this 4 pi epsilon naught small r. And clearly that small r is a variable term, and you can take the limits of this small r as from 0 to capital R. So 0 means we are at the beginning, and capital R means final sphere is formed. So 0 to r. So then this is, you can write this constants outside, 3q square by 4 pi epsilon naught into r power 6 into, see the smaller terms. So here r cube and r square, r power 5, and here one r we need to cancel, so r power 4 you will get. So this is r power 4 dr, and limits are from 0 to capital R. And just simplify that, you will get the self energy of the system. So self energy we can write it as 3q square by, here r power 5 by 5 you will get. So in that 5 you can cancel this 6 here, so that you will get 20 pi epsilon naught into r. And in terms of k, if you want to write 3k q square by 5r. So this is our self energy of the solid sphere. So you need to remember this expression. So we derived the self energy of this spherical shell, and then we derived the self energy of this uniformly charged sphere. In gravitation also you can remember, you can remind that you will get the same expression, similar expression. That means simply minus 3 gm square by 5r you will get in case of gravitation, potential self energy of this solid sphere. So these are the self energy of this solid sphere and the spherical shell. Now let us see how to use this self energy terms and where we need to write the self energy terms. So let us see this. So just write a common question for this. Write the total energy of the total energy in the following systems. Write the total energy in the following systems. So the first example I am taking here. So this is a spherical shell, and here a point charge q is there. This is capital Q, let us consider. This is a shell of radius r. So this is spherical shell, and this distance let us take this as r. That q is a distance r from this. Now we need to write the energy of the system. So you need to remember that if suppose just that point charge I am taking that as, suppose this point charge and q, small q and capital Q point charges, if both are point charges are there. Now the energy of the system is nothing but k capital Q into small q by r, right? This is our energy of the system if only that point charges are present. Because for point charges only interaction energy will be there. There is no concept of self energy for that point charges. And so, but here this is a spherical shell is there. That means which is a charged object. And so now for this, that energy in the sense, we need to write self energy term plus interaction energy we need to write here. So self energy plus interaction energy we need to write. So now the self energy is nothing but, we know already the self energy of this spherical shell, which is k q by, or I can write in terms of constant, that means q square by 8 pi epsilon naught r, this is self energy term, plus interaction energy term. So interaction energy means just we need to write the potential at this point. So potential into, just to remember this, interaction energy we can write simply it as V into Q, where V is the potential at this point into the charge. So potential at this point due to this sphere we can write as Q by 4 pi epsilon naught into R, this is the potential, into the charge we can write here. So now this is the interaction energy. Now this is the total energy of the system. So if they are asking like total energy of the system, then that is the total energy of the system. So that means whenever they are asking, like whenever charged objects are there, if they are asking write the total energy of the system, we need to write the total energy of the system like this, interaction energy plus self energy you need to write. For example, in the same situation the question is given like this. Like suppose I am taking a question like this. This is Q is placed here at a distance of R1. Now we are displacing to this distance here, say at a distance R2. Like suppose we are displacing from A to B. This is a spherical shell of radius R, right? The same situation we are taking here. This is a spherical shell of radius R having some charge Q on this. And this is a point charge, say Q is placed at the point A initially. Now it is slowly displaced to the point B here. Slowly displaced. Now work done we need to write. So we need to find external work done in that process to displace the charge slowly from A to B. So for example, if you want to find work done problems we already solved when we were discussing about the potential energy. Whenever the charged particle is slowly displaced, the work done by the external agent we can write as, we know that work done by the external agent we can write as change in potential energy we can write. So now the change in potential energy is nothing but final potential energy minus initial potential energy we can write. So therefore this external energy we can write as, so final potential energy. So final potential energy I am writing like when it is here, when the charge is here. So I can write this as K into capital Q into small q by R2 minus initial potential energy K into small q into by R1. So that means here, even though we are not writing the self energy, you will get the correct answer only. Even if you write the self energy, you will get the correct answer only. Here actually there is no need of writing the self energy, because here I am not writing the self energy. This term is just like interaction energy only. These two are just interaction energy terms only I am writing. If you want, you can write the self energy terms also, but it will be the additional terms we need to write here. Unnecessary calculation, unnecessarily we are increasing the calculations there. So that means directly you can write the situation like this, because initially this shell will be there, and so whatever its self energy is there, that self energy will be there, and even if you displace the charge to here, there also that self energy will be there, and so that there is no change in the self energy. Initially that self displace some self energy will be there, and finally also displace some this is the final energy. So finally displace some energy will be there, self energy, and initially also displace some initial energy will be there. And so that initial energy, self energy term will be cancelled here, initial and final. So that no need of writing here. So if such a type of problems are there, even though if you are writing the self energy, even if you are not writing the self energy, you will get the same answer. We already solved some problems including the spherical shells without writing the self energy. Like suppose we solved some problems like this sphere having some charge, and we are projecting a charged particle from a very long distance here. So that for example it just grazes the surface, if such a type of question is there. We solved already by applying conservation of angular momentum and conservation of energy, we solved already this question. But in this you can remind that question, in this we are not writing the self energy of this sphere, solid sphere, because initially solid sphere will be there and finally also same solid sphere with the same amount of charge will be there. That means we are not changing the charge on the solid sphere. So when the charge on the solid sphere is not changing, we can conclude that the amount of self energy initially and finally will remain same, and so no need of writing the self energy. So that means in such a problems, no need of taking the self energy concept, right? So particularly if they are asking what is the total energy of the system, or just if they are asking by giving certain configurations, if they are asking the self energy of the system or energy of the system, then definitely we need to write the self energy and interaction energy we need to write here. So it is a concept where we need to write the self energy and where it is not required. And let us take some other examples for these combinations here. This is the one example. Just like I am taking another example as so that means this is say charge Q1 and this is Q2. This is a radius R and this is also radius R, and both are separated by some smaller distance, for example. And now this is having this a spherical shell and this is a solid sphere. That means it is having some volume charge distribution here. It is having some volume charge distribution. Here charge will be there only on the surface here. That's our shell representation. Now we need to write the total energy of the system. Right? So now say this. Now here as a both the charges are charged objects only. So two self energy terms will be there. Self energy of the shell plus self energy of the solid sphere. Plus in addition to that they are interacting with each other. They are at finite separation only. So they are interacting with each other. So interaction energy will also be there. And so that we need to write this as self energy 1 plus self energy 2 plus this interaction energy, right? That means when two objects are there, two self energy terms will be there. When three objects are there, three self energy terms will be there, right? And so that means that depends on this given configurations there. And when whenever charges are at finite distance, then interaction energy terms will be there. And so now here I can write this expression as it is like Q1 square by 8 pi epsilon naught R. This is 3 Q2 square by 20 pi epsilon naught R for the solid sphere. Now see interaction energy. Now can you say how to write this interaction energy here? As I said, the interaction energy simply you can write as VQ. You can take for example, you can assume like this is a solid sphere. This solid sphere is present in the potential produced by the shell you can consider. Therefore, the potential produced by the shell at the center is, we can write it as Q1 by 4 pi epsilon naught into small r. So in that potential the charge Q2 is lying here. Or you can take the reverse assumption also. That means reverse assumption in the sense this solid sphere is producing a potential at its center, then this shell is present in that potential we need to consider here. That means while you are discussing this, we need to write the potential at the center only. That means potential at the center is this shell here we are taking that this shell is producing the potential, some potential at its center, then you can assume that this total charge is lying in that potential you can assume here. And so that is the situation here. K Q1 by 4 pi epsilon naught potential due to shell at its center. Now this total charge is present in that potential we can write here. So that is a now interaction energy term here. So it is when two bodies are there, then that is the interaction energy term calculation. Total energy of the system, self energy plus interaction energy. Now let us take another example for this, another system. Now suppose these two are placed like this. This is say radius A and this radius is B and this is a shell. So now by the diagram you can identify this. Inner one is a solid sphere having some volume charge distribution. This outer one is a shell. These two are concentric. Let us take this as Q1 and Q2, right? So Q1 and Q2. And now here for this system now we need to write here. So here they are separated here. They are separated by certain distance. Now they are concentric with each other. So now let us see the difference there. And so now here again the total energy of the system is nothing but self energy of 1 plus self energy of 2 plus interaction energy we need to write, right? Now the self energy, suppose I am taking solid sphere as a first object there here, or let us take the solid sphere as a first object, then 3 Q1 square by 20 pi epsilon naught A. Its radius we are taking as A plus self energy of the second object. So it is Q2 square by 8 pi epsilon naught B. It is the self energy of the shell plus now see interaction energy. Now how to write the interaction energy of the system in this case? So the interaction energy is nothing but, again as I said, we need to write VQ. So VQ in the sense, suppose I am writing this V on the surface here. The potential produced by this sphere at this point. Now this total charge Q2 is lying in that potential here. So potential due to this solid sphere at this point we can write as Q1 by 4 pi epsilon naught B into Q2 we can write. You can take the reverse assumption also. Reverse assumption means this Q2 is producing some potential. Now this Q1 is lying in that potential. Now this Q2 is actually Q1 is lying inside the spherical shell. So inside the spherical shell potential is same as that on the surface. Now let us see that. Now that potential we can write as same as that on the surface. So Q2 by 4 pi epsilon naught B. This is the potential at any point inside the spherical shell here. So now in that potential this Q1 is lying here. So V into Q1, that gives the potential energy. So then again you will get the same answer. That means we can take any one object is producing the potential. So in that potential the other object is lying there. So you can assume like that. So it is a way of writing this interaction, that means total energy of the systems here. That self energy plus interaction energy of the system. Now let us see this another problem based on this. And actually some more combinations will be there when you are placing the point charge inside the spherical shells. Then induced charges will appear here. About those induced charges and remaining concepts we will discuss after completing the properties of conductors. That means after this we will discuss the properties of conductors. Then in that you can solve some more problems based on this concept here. That means total energy of the system. That means if you are placing some point charge inside a thick shell, having some inner and outer radius different, then we can write the total energy of the system there. So thick shell means further you need to know the concepts of these properties of the conductors. So after completing the properties of the conductors, we can discuss such a type of problems there. And so now here next I am going to derive an expression for write it as a question. A non-conducting disk of radius or write it as the next question. A non-conducting disk of radius r is having uniform surface charge density sigma. Uniform surface charge density sigma in brackets on one side. That means charge will be there on only one side of the disk. Then find self energy of the disk. Then find self energy of the disk. That means previously we derived the self energy of only a spherical shell and like a solid sphere. Now for the disk just we need to derive here. I am asking that as a question. And so to derive the expression for this self energy of the shell, first you need to note the potential at the edge of the disk, which we already derived. Do you remember what is the potential at the edge of the disk? If suppose this is a disk of radius r, then potential at any point on the edge of the disk we can write as potential at the edge as sigma r by pi epsilon naught, right? So that is the potential at the edge of the disk, sigma r by pi epsilon naught. We need to use that formula here. So with the help of the potential at the edge of the disk, you can calculate this self energy of the disk. So now see how to derive this. I am taking a small element in the form of a circular disk of radius r, and this is another ring element I am taking here. Ring element of same radius r and width dr. This is dr. Now similar to our solid sphere. In solid sphere while we are defining the when we are defining the self energy of the solid sphere, there we assume one solid sphere and surrounding shell. So that means just by increasing that, then by adding such a large number of shells, we are getting the solid sphere. We can assume like this. Similarly here, this disk can be made up of infinite number of rings. So infinite number of rings, large number of rings are placed in that with increasing radius. So then here also just I am assuming like this. So just we are adding this ring here with increasing radius so that we will get from 0 to capital R. So during that process we are increasing the we are adding one more ring with increasing radius. So then during that process we are assuming that we are getting a ring of radius smaller, to that we are adding another ring of radius smaller and width dr. So we are adding that ring. So now here we need to write the potential energy of that. So similar to our sphere derivation, let us take here the charge present on this will be, let us take it as Q1 and let us take this as Q2. Now let us write first Q1 and Q2 values. So Q1 is sigma is directly given. So then charge density into its area we need to write here. So then sigma into pi small r square we can write. Then this Q2 is sigma into, that means 2 pi r dr. The area of this ring element we need to write, ring element on which the charge is present. 2 pi r will give the circumference into that dr, that gives the area. Now let us write the interaction energy between these two. So that is nothing but we know potential at the edge. Edge of disk of radius r. So that means that potential we can write as sigma into r by pi epsilon naught. That means I am taking at any point on this edge of this disk of radius r here, then that is the potential. So in that potential this Q2 is lying in that. That means this Q2 is present in the potential of sigma r by pi epsilon naught. And so that now the potential energy we can write it as du is equal to V into Q2 we can write. And therefore this self energy we can write it as self energy of the disk. Just we need to integrate this expression here. So let us substitute this V value, sigma into r by pi epsilon naught. This is our V value into Q2 means we need to write from this. So sigma into 2 pi r dr. This is our Q2 expression. And r is varying from this 0 to capital R. Then you will get the complete ring, complete disk. So just integrate this. Therefore the self energy of the disk is equal to, and the constants you can write outside there. So 2 sigma square by this pi will be cancelled, only epsilon naught will be there in denominator, into the odd terms. Here one r is there and here another r is there. So that you will get r square dr from 0 to r. So then you will get so the self energy is equal to 2 into sigma square by epsilon naught into r cube by 3 you will get. Therefore finally I can write the self energy as 2 sigma square r cube by 3 epsilon naught. So, right? That's the self energy of the disk. That means just we are taking a small element, and for that small element we are writing the potential potential at the edge of this small disk, and in that potential this charge Qt is present. So its energy we are writing here like Vq, and then just by substituting this V value sigma into r by pi epsilon naught, and this dq is 2 pi r into dr, and this pi will be cancelled, and then 2 into sigma square by epsilon naught into r square dr. Just by integrating that you will get this expression here. So that's the self energy of this disk. So it is the self energy concepts, and some more problems we can discuss after the completion of these properties of the conductors there. So in the next class we discuss about the properties of the conductors, and with the help of this Gauss law we can discuss many properties of these conductors there. So then in tomorrow class I will start that properties of the conductors. Thank you.